the last video, then I introduced you to force center, and that reminding you this can be any force or any sum of forces that's causing something to change direction. And that this R is the radius of the circle or the turn that something is making. And then we defined the center seeking acceleration in terms of v squared over r, where again, this is radius. And then I cautioned you that oftentimes you're given diameter instead of radius to make sure that you can, let's just do that, v equals 2 times r, just to remind you, the easiest one to forget. So now let's think about something that's rotating, because I think this is going to be easier to kind of wrap our brains around for some of the values that we need. So let's see. Let me ask you something. If I do this, and I say I have a flea named Linda, put Linda here, and a flea named, I don't know, I should do it in a different color, and we'll call that Skittles. Skittles and Linda. Now, we managed to both hop onto this record that is rotating this direction. This rotating, I mean, we can call it, you guys probably don't even know what these are anymore, 45. So it's rotating at 45, whoops, rotations per minute. So I know that. So this whole disk, when I see this rotations per minute, it says how many times it's going to go around in a circle per minute. And the way I really suggest that you start getting used to writing that would be to write something like 45 rotes, or however you want to abbreviate that, per minute. Whenever you see the per, whatever's following that goes on the bottom. So we now have how many rotations we're making per minute. And now I want to say, okay, so if this whole thing is rotating at that rate, are both of us experiencing the same velocity? Or are they different? So I'm really close to the center, and Skittles is almost at the edge. So pause this and think. What do you think is true? Are we going at the same rate, or are we going at different rates? And if so, who's going faster? So what'd you come up with? So let's think this through. Let's think this through. If this whole thing is rotating at the same rate, let's see what happens then. That means that at the center, doesn't that kind of feel like the center isn't moving? It's just everything's kind of pivoting around the center of this circle. Or if I move slightly further away from the center, I have a really small radius, so a very small distance to cover in the same amount of time that the rest of the thing is making it all the way around. So my tangential velocity, remember tangential velocity is the thing that just keeps pointing straight as we go around. My tangential velocity then, if I kind of line it up with the corner going like that, is going to be really small, because I'm going to complete one rotation at the same time, same amount of time as Skittles, but I just have this tiny distance to cover. The Skittles is all the way over here and has to go gosh darn the entire circle. So at this much bigger radius, Skittles' velocity is going to be greater than mine. And then out here is the largest tangential velocity you can have. So we can use that to think of how do we define this velocity. So let's see, what can I say? I can say velocity then equals, well, we're on a circle. In circles, we always use, let's see, pi r, so this thing gives me the ratio. We say that all circles have this ratio behavior between, the circle radius and the actual, like, going around, so the circumference. So for me to go once around, well, let's see, I come over here, this is pi, come back here, this is 2 pi. So for one trip around. So let's see, that's the distance I've covered, 2 pi r. To make this per second, there's a couple ways I can do that. So there might be a term that you've heard of, hopefully, frequency. Just wondering what that weird noise was. Frequency. And frequency is something per second, so cycles per second. Or you'll see it written as s to the -1 or in terms of hertz. So if I wanted to make this into a velocity, so this is the distance I've gone around, then I would be, let's see, the seconds here is on the bottom. So if I multiply that by frequency, that gives me my velocity. That's how fast I'm going. Or the other one is in terms of period. So period has units in terms of seconds. So seconds per cycle, if you will. So how long does it take to complete one cycle? This one is 45 rotations per minute. So 45 rotations per minute. I would have to turn that into 1 minute as 60 seconds. And that would give me rotations per second. So is that a frequency or is that a period? That would be a period. So I'm sorry, a frequency. As you see, my time unit is on the bottom. So per minute, when it's on the bottom, that's a frequency. If I have something that is just in terms of seconds, that is my period. That is how many cycles are completed in 1 second. So I can rewrite this if I'm given the period rather than the frequency as that V equals 2 pi R over T. Cool. So we also then have a relationship here where I can say that frequency is inversely proportional to period. So I can jump back and forth between these quantities and solve for anything, because the name of the game here is this velocity is that tangential velocity. It's wherever I'm experiencing that. So the further away I am to maintain that same rotational rate, the higher that tangential velocity, the more my center-seeking acceleration. So I've increased the center-seeking acceleration because that velocity goes up.